I hope I'm audible.
Yes, you are audible.
Okay, thank you. So what the plan for today is, we will see some program on how to do supervised learning, and then we'll move on to unsupervised learning and reinforcement learning, and then we'll move on to neural networks, introduction to neural networks. So I'll just share my screen. Okay, so this is some program. I have not written the program completely. Some portions I have taken from some places. So there's one library called sklearn. This library is an inbuilt Python library which helps us use the algorithms for machine learning and implement those in our data. So I have taken this data, Titanic data from Kaggle. If you go to this website, Kaggle, you will be able to read about the data, what the data is. I'll give you a short overview. So in this data, it has sets, training sets and test sets. So what I have done is I have only taken one set and I have divided that into a training set and test set. I'll show you. It has some labels. So what is this? It has the data of the hypothetical data of passengers who were there in Titanic and whether they survived or not. So suppose this is the uh, label we want to actually predict whether the passenger survived or not, and these are the different categories or X values. So P class is what is the ticket class, sex, male or female, age, SIBSCSP means number of siblings, PARCH number of parents, ticket number, fare, cabin number, and so on. So these are different labels it has, and we want to have an idea whether the passenger survived or not. So this is the data I have taken. I have downloaded it and it is there in my computer. So if you come here, it is here. Test CSV, train CSV. So I am only picking one of them, train CSV, and I'm splitting train into two parts. So I'm not using the test part. I'm only training it in the train, some portion of the train, and then using it to predict the other portion. You can use both of the data to check train and test. Okay. So what I'm doing is, first I'm importing some libraries, and this CSV library helps us read CSV files. All right. And there are multiple algorithms I have imported. So these are implementation of the algorithms such as SVM, which is support vector machine, Perceptron. We talked about Perceptron. We did not talk about Gaussian Nash-Bayes, but this is also one kind of algorithm used in supervised learning. And this is K neighborhood classifier. So if you have attended the last class, you might know about support vector machine, Perceptron, and K-neighbor classifier. If you have doubt, you can ask me. I'll just brief you on these. All right. And we will talk about this train test split and standard scalar a little later. And I have also imported random. Okay. So what I'm doing is I'm creating a library for the four algorithms we'll use. First, we'll use K-neighbor classifier. Then we'll use support vector svm.svc. So what is svm? Svm is support vector machine. In that, we are using svc, support vector classifier. So we are using support vector classifier inside of support vector machine. uh, the third we'll use perceptron, and the fourth we'll use naive Bayes. So this is based on Bayes theorem. We were talking about Bayes theorem when we were talking about probability. So these are the four different models we'll build, algorithms we'll implement to do learning in this data, train.csv data, and then we will predict on the other data which we'll have. Okay. So this part is just reading the file. So what are we doing? We are opening this train.csv and we are labeling it as F. So whenever we say F, it means this file has been opened using this variable name F. And these are standard functions in the CSV module. You see, we have imported import CSV. Okay, so we are using those functions dict read. So it is helping us read the file, read the data in the CSV file, and we're creating a list called data empty list. Now what are we doing is this function will give you an object which has multiple items in it. So we are iterating that item in this object reader. So for each row, so what it is doing is in CSV, if you open a CSV file, you will see there are multiple lines, one line after the other. So it is reading one row at a time. So one line and then the next line and then the next line. For each line, we are actually dividing that data into two portions. One is evidence and one is label. So the evidence are X values and label is the Y values. We are trying to predict the Y values in this implementation. So what are we doing? We are in the data, this empty list, we are storing two parts. First, the evidence, and second, the label. So how are we doing it? We are saying we are converting P class into integers. So you see P class, what is P class? P class is the ticket class. So 1 is first class, 2 is second class, 3 is third class. So they are integers. Now we are converting age into float. It can be 2.5 years and so on and so forth. SIBSP, we are converting into int. So what is that? That is number of siblings. So that will be an integer. And we are also converting this to integer, which is number of parents. Okay. So we are just using these four evidences. You can use more also. You can go on and use the others as well. Ticket number, passenger fare, cabin number. We are just using four for simplicity. Okay. We have four X values and the Y values is survived if row is equals to 1, else not survived. So you come here, you can see if it is 0, then it has not survived, the passenger has not survived, and if it is 1, then the passenger has survived. Okay, so this is how we are pre-processing the data. These are just pre-processing the data. Okay, we have pre-processed the data and we are saying X. Now we'll use X as the evidence. So what we're doing is we are creating a list of list. So this X will be in the form of list of list. I'll show you how it will be. So suppose this will be a list inside a list like this. And each inside list will contain the values in that row. So the value of passenger class, comma, age, comma, number of siblings, comma, number of parents. So it will have this. So suppose the passenger class was 1, the age was 20, number of siblings were 2, and number of parents were 2. So this is the one element of the outer list. Similarly, you will have another X. So these are X values. This is one X value. Yes, yes. You can just
Shubham,
unmute. Yes, yes.
Data in the data dot append in the evidence, we just calculated means we just calculated the available data like class of a passenger, age of the passenger, sibling, number of siblings or spouse, or number of par ch if okay, parents, etc., etc. But when I say int into bracket row p class, it will
Yes.
count number of, it will count type of passengers like class 1, class 2, or class 3, correct?
No, no, I'll just show you the CSV file first, maybe. So let me just show you the CSV file. Where is it? It is here, right? ISIS. Okay. It is here. Train.csv. So it has rows. So when I say row in bracket age, so it will give you 22. When I say row in the box bracket, so when I say this, when I say row, so what is happening in reader? Reader is getting all the lines, and for each line, for each row, it will have the value of P class row. So what is P class row for the first row? Which is 3. For
3.
the row age, it is 22. row SIB SP is 1 and so on. So these are the values the first element of this data will have. This evidence will contain the first row. For row is equals to 0, for row is equals to 1, again it will append the data to it, right? If
So
you're not able,
evidence is a structure which collects the data for that particular row.
for all the rows, I'll show you, I'll show, yes,
Uh-huh.
for that row, right, for that
But
row.
where that red data is stored means
I'll
it
show you
definitely.
just a split cell. So what is happening is I'll just kernel restart and clear output. Okay, so we have run this, and we'll just go here and say data 0. So what is it has? It is a dictionary. The first element has a key called evidence, and it has the values. So the first value will be p class. So you see row 0
Class
has p class of 3, right?
age
um,
2.
it is 22.0 and so on and so forth. If you data com 1, sorry, if you say data 1, okay, then it will give you the second row. So you see second row p class is 1, you can go and check second row p class is 1, age is 38, you can come here and see age is 38, like this. And the label was survived. So if you go there and check whether it has survived or not, so you see it is 1, which means it survived. Okay.
So I have one very basic question. Means where shall I find that particular variable in the Python?
Which variable?
Means for example, if I only execute int into bracket row p class,
Right.
only one line. Let us assume that we are executing only in yeah, only this line. Then
Yes.
the answer that I'll get is for a particular, for first row I'll get 3 answer, correct?
Just a minute. You see, when I
I'll get answer is 3.
I'll show you. So inside the for loop, I'll print this, right? So what will happen is I'll just say break. What will happen is it will run for each of the row. So for the first row, it will run. So I'll say is row, comma this. So you see for the uh, what is happening is, okay, row, I cannot say row. It will give me the row values. So I'll just say this. So what is happening is for first row, it is going to read what is there in this label, which is
Okay,
P
correct.
class. If you
Where
just
that
print
range
the row,
data is stored?
it is inside this reader.
No, stored in the sense by what name of variable it is stored. For example, in C programming, when I define int C and when I write C assign the value of 3, then 3
Okay.
is stored likewise.
So you see why this int is not the int which you are thinking. This is actually a conversion. We are converting explicit conversion. So whatever the value of this int is actually a function which is converting the value of this into an integer. So it is explicit conversion of data.
Okay.
This float is explicit conversion of data to float. These are type conversions.
Okay.
I hope you
Means
get.
no, not clearly. Let me once again put my
So why are
question.
we doing this? Just a minute. Why are we doing it? Suppose this data was a string. So what will
Uh,
happen? We cannot use it to do this machine learning thing, right? So we want to convert that thing into number. That's why we are
no,
using.
I got the intention that why are we using int, float, etc., etc. My question is, if let us assume a is let us assume a integer a as value 3, integer b as value 4, and if I perform a plus b without assigning any new integer, then by what name in Python the answer 7 is stored?
It will not be stored. So you are saying a is equals to 3 and b equals to 8, and I say a plus
A
b.
plus b. Uh,
It will not be stored. It will not be stored. We are just printing the value of a
Okay.
plus b.
That is,
We are just, it
please
is just,
repeat last sentence.
it is just lost. It is just over here showing you the value of a plus b, but it is not printing. It is like it is
Okay.
lost in the memory. It has done the operation, but that value 11 is lost in the memory.
Okay. Clear. Okay.
Okay, so we have this data. Now what we're doing is we are separating that data. So for y we are for x we are separating the evidence, and for y we are separating the label. Now what are we doing is, so we are using a inbuilt function called train test split. Instead of that, you could have also done it yourself. You could have said that 70% of this data I'll use to train, and the 30% of the data you could use for test. But we are using a function which helps us do the same. So we are passing the capital X, this why are we writing capital X? Because it is a vector. Okay, and y. So we are giving x comma y, and we are saying test size is 0.7, and this random state is actually kind of so random numbers when we generate in computer, it need not always be random, because that there is some technicalities there. So when you change this from 42 to some other number like 50, this which 70% of the data will be split, that will change. Okay, so that is why we are using this 42 over here. That is not very important right now. So what are we getting? 70% of the x values are coming in train, 30% of the x values are coming in x testing, again for this and this. Okay, so respective values we are getting. So this just splits the data into two parts, into train and test. Now this is where the model is being built, and then we are testing it. Forget the for loop for now. Okay, so what are we doing? We are saying model dot fit. So what is the model? You see, I have created a okay, for simplicity, what I can do is, just for simplicity, I'll just copy this part, I'll paste it here, and I'll copy this part and I'll paste it here. Sorry, I'll paste it here. Now what I will say is, I will say just give me a minute, huh? So this is it. Let us use this. Okay, so what I'm doing is I am saying model name is equals to perceptron, that is an uh, string, and model is equals to this perceptron. This is a keyword right now. So when I say model dot fit, what it means is perceptron dot fit. Okay, and what it is fitting, it is fitting the x train with y train. Okay, and then we are, so we can split that cell over here to better understand it. So when we implement this, first let me run again. So I'll clear all output. I will run this. So you see, we have built the perceptron model. When I say model dot fit, so what is model? Model is actually perceptron open parenthesis closed parenthesis. And when I say model dot fit, it actually means perceptron dot fit. So model is just carrying that thing. So it is just means perceptron dot fit. Okay, and this is the model. This is actually the model. Okay. Now what I will do is I will use this model to do the predictions. So model dot predict for the x testing values. So when I say model dot predict and I'll pass the x testing value, so these are the predictions it has for y values. Okay, so I'll again split the cell to better understand it. So when I run this, prediction stores all the predictions made by this model. Model building is only done by only this line. The model is built. Now when I say predict, it predicts the value and it is stored into predictions. Now I'll just calculate how many of the values are correct for this prediction. So what I'm doing is, I have y testing already, I have y testing and I have y predictions. In this line, I'm just checking if this value is equal to this value. If that is true, then I say 1, and if it is not true, then it is 0, and we are summing it up. So you can do it in multiple lines. For example, you can say for this comma this end, zip. So what you can do is for this comma zip in zip, what I want to do is I want to check if actual is equals to predicted, right? And I can say count is equals to 0. So if this is true, I can increment count plus equals to 1. So it means whenever actual value, what is actual value, y testing value, is equal to the predicted value, then we are incrementing the count, and at last we will just print the number of count values. Okay, you see 384 we have predicted to be correct, and how many values were there, you can just check by obtaining the length of y testing. So you can see there were 624 values. Out of 624 we have predicted 384 correct, right? So the same thing I am doing over here. Okay, so you see we have correctly predicted 384 out of 624, and when you divide it comes out to be 61.54%. So the accuracy of the model is 61.54% using this Perceptron model. Okay, now we had a for loop. So this is complete. Before going forward, this is complete. So what we did, we did pre-processing. We extracted the data from the CSV file. We labeled it as x comma y. Now what we are doing is we are splitting the data into test and train. When we have the testing data, we build the model using the testing data of x and y. Then we do the prediction, and then we check how many of them are correct and how many of them are wrong, and therefore we obtain the accuracy. That is it we are doing here. You can use any kind of data, make sure it is labeled properly, and then you can do. And over here we have used this Perceptron model. Instead of Perceptron model, you can use other models as well. You can use the support vector classifier, you could use the k-neighbor classifier, you can use Gaussian naive Bayes, and so on and so forth. Okay, any questions? Any questions? All right, so what over here I am doing is, over here I am iterating. So I am saying I have 4 models, let me iterate over all the models. So this models, it is actually, you see it is over here, it is a dictionary which contains the key and the value. So for the first for loop we will run k neighbor classifier with n is equals to 3. For the second for loop we will run support vector machine. For the third classifier we'll run the Perceptron, and for the fourth we will run the naive Bayes. So 4 models will be run simultaneously using this for loop. Everything is same. If you read properly, you see this model will get one by one the models, and then we can just fit the model, predict, and do the calculation how many, what is the accuracy of the model. So when I run this, you see first it is using k neighbor, k nearest neighbors, right, k neighbors, and then it has an accuracy of 64.74%. For support vector machine it has an accuracy of 60.9%. Perceptron model it is 61.54%. Naive Bayes it has an accuracy of 67.31%. Not very good. Your accuracy should be around 98-97%. Nevertheless, it depends upon the data and moreover the model you are using. You can change the model as well. So for k neighbor classifier you can change it to 4, 5, 6, and you can see which number is giving you good accuracy, and so on and so forth. That is not important right now. The implementation is important. So is the implementation clear? All right, now you see over there I have used this train test split. It is helping us to split the model. Now what I will do is, just a minute, yeah, so what I will do over here is I will split the model myself. That you can do as well. So in this code everything is same. I'm just splitting it myself. I'm saying holdout is the first 70% of the data. So I'm not randomly taking 70% of the data as the function was doing. I'm just saying take the first 70% of the data. and then okay, I am randomly shuffling it later. So what I'm doing is I am saying what is the holdout. So suppose there are 684, this length will be 684, right? So 684, and I'm saying what is the value of 70%, so 0.7. So we are getting 478. So this holdout will have a value of 478. And now we randomly shuffle the data, and then we say from the starting to 478, that will be my testing data, and from 479 to the rest, that will be my training data. So we are doing it just by ourselves. Over there we are using the inbuilt function. Okay, then we are saying training data, testing data, training data, testing data, because this we have to do ourselves. Over here that was done by this function itself. So we were just passing x and y. This is giving me separately the x training, x testing, y testing. Over here that is not so. We have to make ourselves the x training, x testing, y testing. This is little bit cumbersome. You can use simply that train test split. I just wanted to show you what that function is doing. So this is what that function is doing. Okay, in the higher level there are other details also, but higher level this is what it is doing. Now this is something new, scalar, standard scalar. So you see over here we are standardizing the values of the this data. So what does it mean? So you see, whenever you have data, suppose we can come over here, this uh, age can vary from 0 to suppose 60 or 70. This ticket number will have different range. Cabin number will have range from 0 to 20, 30, 40, so on and so forth. Passenger fares can have other ranges. So all these data have different ranges. So this will influence your model accuracy. So to counteract that, we standardize the data. So over here, we are using normal distribution to standardize the data. It's like normalization. We are bringing all the data into in the same scale. So for when we are doing normalization, we are putting all the data from 0 to 1. And when you are using standard scalar, it is just normalizing the data with the mean and variance, same mean and same variance. Okay, and everything else is the same. So we are just saying scalar dot fit transform. So we are transforming this x training data into that standard scalar form, and over here also x testing, it is getting transformed into this
Shubham,
standard form. Yes, yes.
because the data has a, for example, say data type integer or float, we could be in a position to normalize it. But had it been, for example, say non-integer like name or something, how could you standardize that data? Means,
So we will
uh,
not be able to use machine learning then, right? It has to be numbers. If you go back and remember, we had random variables, and those has to be
uh,
numbers to. So you have
okay.
to convert those values to numbers. Otherwise, you will not be able to do this kind of training.
Okay. Means the data has to be in a numeric form. It cannot be in a
Yeah,
alphabetic form.
we
Okay.
are because that is easy to handle.
Hmm. Okay.
And again, everything is being done same. So we are just fitting that data, doing the predictions, and then checking how many of them are correct and printing it. So this is just the same thing. So you see, after standardization, support vector machine is doing better. Just an observation, nothing concrete right now. It is just dependent upon the data. So we can see that the support vector machine did better over here. It is not, I'm not saying that it will always do better in any kind of data. We have just observed that support vector machine is doing better. And yeah, so this is the same thing. So everything else is the same. You go through, I'll give you the code, and this is how we use this sklearn to perform the algorithms or to use the algorithms of machine learning and then implement it in our daily life. Is that all right? If you need more data sets, you can come to this website Kaggle. It has a lot of data sets in different categories. You can use those, and it is a well used website. You can come there and you can see. I'll provide I'll provide the code of this, whatever we have done over here. Is it all right? Okay. So what I'll do is I'll come back and I'll start with reinforcement learning, and then we'll go to unsupervised learning. Okay. So what is reinforcement learning? So in reinforcement learning, so in first of all, in supervised learning, we required data, and from that data, the agent learned, and then we did predictions, right? In reinforcement learning, we do not require data. The agent learned from its environment. It interacts with its environment and then learn. So suppose think of it like a game. So suppose you have a game. For example, you can think about as tic-tac-toe, and that agent is interacting with that grid, and it is learning by playing. So whenever he fails, he has a reward of some -1, and whenever he passes, he has a reward of +1. And for each of the actions he is taking, he can see which action leads to what state and what is the ultimate reward he is getting. And when doing multiple times, in hundreds and thousands of times, the agent will be able to learn what is a good move at each of the state, and then it will become better at playing the same game. So that is how that is an example of reinforcement learning. So that agent learns from it interacting with its environment. All right. So it can be chess as well. So you can let a agent play the game multiple number of times, but chess has multiple states, and that's why it is difficult to train an agent using this simple idea of reinforcement learning. There are different algorithms, high level algorithms to implement such kind of learnings, but nevertheless the idea remains the same. So suppose you have some kind of game where you have obstacles, and you are required to pass this obstacle. An agent is required to pass this obstacle. So it can just randomly start with going. So you can have to specify the actions it can take. So suppose the agent is here, this is the first state it has, and the action can be go left, right, up, down, something like that. And it can just go up and down and check whether he is getting a reward or not. And doing this multiple number of times, it can learn its environment, and then it will be able to perform well after some number of iterations. So a machine learning paradigm where the agent learns from interacting with an environment. The agent performs action to maximize the cumulative reward. So when I'm saying cumulative reward, it can happen is at each state it visits next, it can get a reward. So for example, in tic-tac-toe, a reward structure can be if the opponent did not win in that stage, you will. So what I'm saying is, suppose this was the tic-tac-toe game you were playing, right? If you did something like this where you did not let the other player win at the next stage, then you will get a reward. So each action can give you a reward. Okay. So cumulatively you can get 7, 8 some reward for this game, right? So that's why cumulative rewards come into play. So what is it is based on feedback, reward and penalty, positive feedback for desirable outcome, negative feedback for undesirable outcome. So there is no predefined label. Instead, the agent explores and exploits to improve its strategy. Any questions? Okay.
No.
Okay, so we can think this as a Markov decision process. We have talked about Markov chain, but this is a little bit different from Markov chain. Why? Because in Markov chain, we had states and actions, right? So we were in a state 1, we can go into state 2, where using action. So that action over there was time. So at time t is equals to 1, you were at state 1. You can go to multiple states, but at time is equals to 2. So this action was fixed. You always had to move forward in time. In Markov decision process, you have a set of actions to take. So you can either move forward, or you can move back, or you can have multiple actions from one state. In Markov chain, you always had one action, move forward in time, right? In Markov decision process, with states, you also have a set of actions. You can decide what action you can take. So we uh, drew Markov chain as S1, it can go to S2, then it can go to S3, and so on and so forth. This S2 can have multiple states, but in Markov decision process, from S1 you can take multiple actions. So you can take action 1, action 2, action 3, and you can go to different states, right? So for example, in Markov chain, you had one transition probability. So for S1, S2, S3, S1, S2, S3, and this transition probability was fixed. Now in Markov decision process, you can have different transition probabilities. This transition probability is for action A1. You can have another transition probability for action A2. You can have another transition probability for action A3. The states are same, but different transition probabilities for different actions you are taking. So that is the idea of Markov decision process. There are different states, but there are different actions as well. Okay. And transition function. So from this state, if you take action A1, with some probability you can go to S1, with some probability you can go to S2, with some probability you can go to S3. Okay. So that is the transition function. So you have to specify all the different transition probability matrix, then only you will be able to see what is the transition function. There is one more thing which is different from Markov process, is the reward function. So from each state, if you go to another state using a function, you will also get a reward R1. So with a transition probability, you also have a reward structure. It takes the input at which state you are in and what action you are taking. It will give you the reward. So for example, if you are thinking about a maze problem, that will be easier to understand. So suppose you are thinking for a maze problem. So you are here and you want to come over here, right? And what are you doing? There are some obstacles. So this is one obstacle, this is one obstacle, this is one obstacle, this is one obstacle, right? Now think that you are at this state. So this is state 1, and you can take from this state 3 actions, either move up, right, or down. So for each action and at that state you can get a reward. So if you move up, you get a reward of -1. If you move right, you get a reward of 1. If you move down, you get a reward of 1, so on and so forth. So each action at each state will give you a reward. And we'll talk about discount factor. What does it mean? We'll talk about that. Okay. Is it clear? Let me not erase this. Is it clear? All right. So what is a discount factor? Discount factor is if you are getting a reward now, you may value that reward more than you get the same reward at a later time point. It's like money. So if you get 100 rupees now as compared to 100 rupees 1 year later, you will value that 100 rupees today more. So that is the discount you are applying to the value at later time point. That is the factor which I am saying. Uh, Gamma. Why are we bringing it here? Because we have some kind of reward, and if you get a reward now, you will value that reward more as compared to a reward which you get at a later time point. That is why we are bringing this gamma over here. If you have read about this kind of things, you will be able to understand it very easily. Okay. What is the objective? Our objective is to maximize the expected cumulative reward. So over here we are saying at each action from a state you will get a reward, and you are trying to maximize the cumulative reward, expected cumulative reward. Okay. Now we'll see how we are solving this using a maze problem. Okay. So we have talked about this reinforcement learning. We have talked about maze solving. An agent navigates through a maze to reach the goal while learning an optimal policy. Key components: the environment. Over here the maze is the environment. Over here the states are the different positions in the maze. Actions can be up, down, left, right. Reward strategies can be positive reward for reaching the goal, negative reward for hitting a wall. You can have other reward strategies as well. So you can have positive reward if you do not hit a wall, and so on and so forth. One more thing I missed out is the transition states. So this transition function, I mean, sorry. So transition function. So what is the transition function? That maze is actually the transition function. From that point, if you're going up, so you will come over here. If you're going right, you will come over here, and so on and so forth. Is that all right? Okay. So I'm assuming it is all right, right? Yeah. Okay. So steps in reinforcement learning, we have talked about this initializing the environment. So we have talked about how to, so now it becomes formal, right? So when you formalize this idea in programming, you have to be very formal. So this is what it is. Initialize the environment, define the maze layout, states and possible actions. So whenever you are programming, you have to define how are you representing that maze. What, uh, how are you representing the states? How are you representing the action? What action will lead to what reward? That transition function, you have to specifically code that into your program such that you will be able to use it, right? Define the reward structure, so that you have to define that function, and you have to say at what state with what action what will be the reward. And choosing the algorithm, so we will learn about q learning, but there are other algorithms as well to solve to for reinforcement learning, but we'll only talk about q learning. We will see what q learning algorithm is for reinforcement learning. Then we will train the agent, so it will explore the maze and update. So we will see how the agent updates q values, right? And okay, so what we'll do is, first for that maze we will say initialize some q value. So suppose we are initializing the q value for all the states are 0. So it is like the expected reward value. So initially we don't know anything about the maze. So we are saying the expected reward at each of the state is 0, right? For every state, the expected reward is 0. And suppose the start state is this. Now what it does is the agent, it explores the maze. So at this state S, it takes action A. So what is the state? This is the state it is in S1. And suppose it takes action A1, right? It takes action A1. So how will we update this Q S1 comma A1? So what the expected reward at this stage, it will say QS comma A is equals to QS comma A, whatever I had knowledge earlier of that state, plus alpha times the new reward I am getting minus the old reward. So it's like the difference. I thought I would have got this Q value, QSA, but I got this value, whatever it is, I'll tell you what it is. And I will update it the difference. So suppose the earlier I was assuming it to be 10. Earlier I was thinking it is 10, but I got 20. So what it will get? 20 minus 10, the difference is 10. We will add alpha times 10 to this 10. So it will become 10 plus alpha times 10. Why alpha? It is learning factor. You can think about it as if it is 0, then you are learning nothing. You are always assigning QSA to QSA. It means you are not learning anything. If you are setting alpha to 1, then you are forgetting the previously learned value. You're just saying whatever I'm getting now, I'll just accept it. So this 10 will replaced by 20. But when this alpha value is between 0 comma 1, you are getting a value between 10 and 20, right? So some kind of learning factor. Okay. So this is how we are updating this QSA. Now the question comes, what is this value? What is this value? Okay. Before we discuss about this value, is this clear how we are updating the expected value at each of the states?
Hello, Shubham.
Yes.
Why minus QSA? Why not plus QSA in the
So,
formula?
so Q S comma A is equals to Q S comma A plus alpha times whatever we are getting right now minus Q S comma A. So this is the difference. Achha, suppose alpha was 1. So if alpha is 1, you see these two will cancel out. And we will only have the reward which we got, right? So we are saying QSA is just equals to R. So this is actually the difference. I have thought that I will get 10, but I got 20. So I have to add something to this 10, right? From 10 to 20, that is the range. I have to increase 10 to some value, but not more than 20. So this function will help you do that, right?
But
Got it?
in the formula, it's not QSA equal to, QSA tends to.
No, no, this is actually, so I'll tell you what this is. So when I write like this, in mathematics, it is different. In programming, it is different. What this means in programming is assigned. So you see, I'm using that same value in two different places. In mathematics, it is not correct, right? So if I write like this, x is equals to x is equals to x plus 3. This doesn't mean anything, right? In mathematics, this is wrong.
Hmm. Hmm.
Right? So this means assigned to. So in computer, so when we write coding, we just say x is equals to x equals to 3. So this is assignment. This value is stored in this value. So this arrow means whatever this value is, it will be stored in this, assigned to whatever is in the left.
Okay. Okay. ठीक.
Now coming to what this value should be. So you see, this value should be first R. So when I'm going from this state to this state, I will know what the reward I get because I will call that reward function RSA. So this value will be first RSA, that value. So I'll write the whole function for better understanding. So it is Q of S comma A will get Q of S comma A plus alpha times, I'll write this, minus Q of S comma A. So uh, when I was in S and I moved to some other state using a action A, I will know what reward I get because I have called that function R S comma A. That is the reward I am getting. But this is not only, I'm interested in not only this value. You see, suppose there was a wall in these three cells over here, over here, over here, over here, and over here. There were three walls. Now, suppose going over here gave me a reward of 10 or 20, suppose 20. But after here, I cannot go anywhere. So I should also consider future reward from this state. What will be my future reward? So that I have to add. So this is that future reward. This is the immediate reward I am getting from moving from this state to this state. And this is the reward I will get when I move away from this state. Okay, so I'll repeat again. This is the reward I got when I moved away from state S, plus I have to add one more reward which I will get when I have moved away from the new state I went. So that is this reward, and I am discounting it with factor gamma. Why? I will get it in the later time point. That reward I will get at one state later, and that is why the discount factor we were talking about. What is that discount factor? Okay. So this discount factor will be multiplied to the future reward I will get. And I'll talk about this function. Before that, is it clear? The current reward I am getting plus discounting the future reward I will get. Is that clear? This expression is not that important. The idea should be clear. Right. So now what is this expression? It just says whenever you are at S dash, you can take multiple actions, right? So you can take A1, A2, A3, multiple actions. Whatever reward you are getting, which is maximum, you take that. So suppose you are over here, you get from going to here you get 3, you from going here to here you get 4, from going here to here you get 5, right? So you choose that value which is maximum because you will always do that. If you get 3 in one side, 4 in one side, and 5 in one side, you will always go to 5 because you know you will get 5. That's why I'm taking maximum Q S dash A dash, maximum over all the actions at S dash, right? If it is not clear, please let me know. So in this new state S dash, I will take that action which will maximize Q, because I can get the maximum value. Why shouldn't I take the maximum value? That is why I'm taking maximum. This is the expected future reward. And I'm multiplying with the discount factor, this gamma, and adding it to R. So this is the complete reward I will get when I move from S to A. Sorry, S to S dash using A. Okay, so this is that Q value, and that is why this is known as Q learning, because of this Q. Okay. So these are all the things, the notations which we have used. What is goal? Goal is to iteratively update Q value such that, so what will this agent do now? So we have talked about Q. Now think, what will this agent do? First, it will start with some point. It will start from some point. It initializes Q values as 0 for all the states. It goes here, it comes here, it comes here, it comes here, it comes here, and it goes here, right? And it sees that it has got a reward of some, suppose 7.5. Now it will come over here, and then it will get a reward of -1. Then it will come here, it will come here, it will go here, and it will get a reward of suppose 0.2. And it will explore this maze multiple number of times. And when it has done that, it will see what is the best reward I could get. It is 7.5, so it will take that step each and every time after some number of iterations. Is it all right? Right. Now you see, this is a deterministic kind of thing. You see, suppose the agent has come over here, gone over here, and for the time being, suppose there was more blocks. Suppose there were more blocks. To make you understand one idea, suppose there are more blocks. It come over here, then it came over here, it came over here, it came over here, and randomly it went this side, right? Now you see, initially it has assigned 0 values to these. And when it saw that this steps which I have taken gives me some reward, suppose 7.5, it will always tend to take that action. Why? We are always maximizing. So whenever it is in this state, it will take that action which is maximizing its reward. So it will come over here. Again, when it is over here, it sees that it is 0 and it has some positive value. It will always take this step. And again, it will always take this step. So there has to be some randomization. That, what is the randomization? It will take greedy value for some number of iterations and non-greedy value for some number of iterations. So it randomly explores some new states as well. It shouldn't take always the maximum Q value. So first it will obtain the Q values, and the algorithm will say, don't always go for greedy Q. You can take non-greedy Q as well for some number of iterations. That will help you explore the maze more. So we talked about exploration and exploitation, if you remember. Exploration and exploitation. So when you explore the maze, there has to be more randomness. But if you exploit whatever you have learned, then the randomness decreases, right? In simulated annealing, when we are talking about such kind of things, if you remember, if you recall, whenever the randomness you want more, then you are exploring the whole neighborhood, the whole, not neighborhood, the whole landscape. And when you are exploiting, you are coming to one area and you are just trying to fine tune the things, right? So whenever you are trying to explore, you move some random steps, you take some random steps such that you are able to understand your landscape. Is that all right? Is it all right? Am I audible? Okay. So challenges. So we should balance between exploration and exploitation, right? Handling large and complex mazes with sparse rewards can be done. Computational cost of training. So there are, so what is happening is, when the maze becomes large, then the computational cost increases. Applications, you can think about a lot of applications like robotics when it is learning the area. So for example, a robot has gone to an area where it has never seen that area. So you take example for that vacuum cleaner. So when you have purchased a vacuum cleaner and you have placed it in your home, that robotic vacuum cleaner, it explores the area it has to do the sweeping and cleaning, right? So it uses this kind of learning to map the area it has to clean, right? Video games, operations research, and there are other areas as well where this kind of reinforcement learning is required. You don't need data to do reinforcement learning. You can just explore your environment and then become good at it. Okay. Now, what is unsupervised learning? So we have talked about supervised learning. We have talked about reinforcement learning. We are talking about unsupervised learning. In unsupervised learning, you do not have labels. So when we were talking about just right now, X values and Y values, there was someone who has labeled the data one by one. The Y values were there, right? In unsupervised learning, we don't have the Y values. We only have X values. And the computer has to understand that data and do some kind of learning in that. So for example, classification task, not classification, sorry, clustering. So you can have um, like survived and not survived. So you have some kind of data and you don't know if they have survived or not. So you can ask unsupervised learning algorithm to do that. I'll give you more better data. So suppose you're trying to understand how a dog communicates. So you have the audio waveform of lot of dogs, a lot of data you have, the audio waveform you have, and you also see observe what the dog is doing next. So it has heard this audio waveform and what is the reaction of that dog. So you can plot it in not plot it, you can register the data in some data sets and pass it to unsupervised learning algorithms. It can learn from the different communication audio waveforms and it can group that whenever this kind of audio waveform is transmitted from animal 1, this kind of audio waveform is heard from animal 2. So these kind of communications where you are not able to label the data can be learned from unsupervised learning. Okay. So focuses on understanding the data structure without predefined categories or outcomes. You don't know what are the categories, you don't know what are the outcomes. Still you want to understand the data. So for understanding the data, unsupervised learning becomes important. Okay, so for unsupervised learning, we will only see clustering, but there is one more thing which is known as dimensionality reduction. So I'll give you one idea of dimensionality reduction before we move on to clustering. So suppose you have some data for supervised learning. For example, we are doing supervised learning. This is X and this is Y, right? Now for X values, you have millions of rows, columns, millions of columns, right? And you want to do supervised learning. Now, if you want to do supervised learning, you have millions of columns that X values have millions of values and you want to relate it to one Y value. Just think about how large, vast the data set can be. But if you think about it, if those many millions of columns are there, some columns may be highly related to the other. So some of them are very closely related. It is just classified into two rows, but they are very highly related. So what you can do is you can do supervised learning in the X data and you can reduce the number of columns it has. So suppose it had 1 million column and you are reducing the dimensions of that column. So you have reduced it to suppose 10,000. And then you can use supervised learning to learn from this 10,000 columns and why. How are you doing it? You are merging some of the data. You are saying we will merge these values into one column, x1 dashed. We will merge these columns into one and it will become x2 dashed and so on and so forth. This is known as dimensionality reduction. We don't know which columns are related, but this unsupervised learning algorithms helps us to merge some number of columns and reduce the dimensions of x value. Is that all right? Right. Now we'll talk about clustering. So what is clustering? We're grouping data into clusters based on similarities. So you can have different kind of data and you are trying to cluster similar data, right? Common algorithms, k-mean clustering, hierarchical clustering, and there are many other algorithms as well, but we'll just talk about k-mean clustering. Applications, customer segmentation in marketing, document categorization, or for example, you are trying to understand reviews, whether it is a positive review or negative review. So you are giving lot of reviews to these clustering algorithms, and it will tell you that these reviews tend to be positive reviews, these reviews tend to be negative reviews. You have not labeled the data. You're asking the unsupervised learning algorithm to cluster the data for you into two categories, positive and negative. You can have multiple categories as well. So in scale of 1 to 5, 1 is the best, 5 is the worst, and there are different other levels. So you can have multiple categories of reviews as well. So that clustering can be in 2 groups, 3 groups, and so on and so forth. So how this k-mean clustering works, before going into the whatever I have written over here, let us understand it with one diagram or example. So suppose you have this data, and first you have to decide how many clusters you want to have in this data. So that is a difficult question to answer. So you have to explore. First you have to pass 2, then you have to pass 3, pass 4, pass 5, pass 6, and check what is the error you have. I'm not going into that. We can talk about it later. But for now, suppose you have already thought about, say, there are 3 categories in this data. Mind you, this is a 2D data set. You can just see and tell, okay, it looks like 3 categories. But if the uh, dimension of this data is n, where n is very large, 4, 5, 6, 7, and so on and so forth, you'll not be able to visually categorize the data, right? So for understanding purposes, we are just looking into 2D data. Now, for some reason, you have thought that there are 3 clusters in this data. So what we'll do is we'll randomly put 3 dots. So first I'll put red over here, green over, sorry, blue over here, and black over here. We'll randomly put 3 dots. This represents centroid of some data. We'll talk about which data it represents. So we have 3 dots right now. This is black, this is blue, and this is red. Now you obtain which points are closest to each of these. So you see these points look closest to red. These points look closest to blue. And these points look closest to black, right? Right? And maybe this also. So just a minute, maybe this as well. And this is what black looks like. Okay, so this is how, because we have randomly put these 3 dots, so this is how we are taking whichever is closest to the centroid. So we are saying this is the centroid, right? Now what you do is we obtain the new centroid. So you have these dots you obtain the new centroids for these dots, and you move these dots to the new centroid. So what you do is, for red it will move maybe here, for blue it will move maybe here. Sorry, blue, I should use blue color. And for black maybe it will move over here. Okay, so you're just moving the centroid. Now you should erase whatever categories you have made earlier and repeat the steps, right? So again, see which points are closest to which. So I guess red are closest to this, blue is closest to this, and black is closest to this. And again compute the centroids, and then again move the centroid to that new centroid, and again do this, repeat this some number of iterations until your centroid do not move a lot, and then you have categorized the data into the number of categories you have given. So this is how k-mean clustering works. Any doubt?
Shubham, that movement of centroids, is it a manual intervention or it is done by computer or programming?
So we have, what we are doing is, again I'll just repeat. So first we have put some centroids, right? And we are saying this centroid, these data are closest to this centroid. Okay. Now what will we do is we will obtain the new centroid of the red points, because we have labeled these points as red points. We will obtain the centroids of these points. So suppose the new centroid of these point is this, right? So this centroid will move to this new point, and when it has moved to this new point, I will again check which points are closest to this red point. So these points.
That's my question. That's my question. When you said in this instant case, when the red centroid moved to the new position, how it is moved? Is it moved by manual intervention or computer programming will do that motion?
So what in computer what it is done is, when I'm saying my earlier centroid is here, it means xc comma yc is equals to suppose 1 comma 5. Just replace x c comma yc by 2 comma 3. So this replacement is done by functions. You just say compute the new centroid, assign x c comma yc comma whatever the new centroid is. This movement is just assignment of that value to the new value,
Okay. Okay.
right? We're just
Okay.
assigning. Earlier xc comma yc was 1 5. Now xc comma yc is 2 3, and again it will change to some value. We're just reassigning values.
Okay. So initial locations of centroid is determined by.
What is randomly? You can do just randomly.
Okay.
There are other better algorithms as well, but for understanding, you can just randomly distribute that centroid into some regions. There are other intelligent algorithms as well, but for understanding, I'm saying you can just distribute the three centroids anywhere in the plane.
Okay, no, the reason behind asking this question was because in the instant case the graph is visible. Many a times it is the case that when we do not have clear picture of distribution, in that case, how to locate the centroid?
So what you can do is you can check what are the farthest point from each other. So you have n dimensional data, you have to have n dimensional distance. So that is known as, so that is can be obtained like this: n root of x1 comma x2 plus to the power n x1 comma x3 comma n. Like this you can obtain the nth distance. Like square distance, how do you obtain? X1 comma minus x2 whole square plus y1 minus y2 whole square. So you can extend this idea to n dimensions. Okay, so you obtain the distance, you know what is the farthest points, and you can take your centroids inside that whole hyper volume, right? You'll create a hyper volume in higher
Okay,
dimension.
clear, clear.
Over here in this k-mean clustering, the most costly step is to obtain which points are closest to this point. Why it is costly? You see, to obtain which points are closest to this centroid, you have to take the distance from each of the point, right? For each point you have to obtain what is the distance for the red points. For each point you have to obtain what is the distance for the blue point. For each point you have to obtain what is the distance from the black point, right? For each point you have to obtain, then only you can say, then only you can say um, that okay, this point has a red value of 2, black value of 5, and blue value of 3, so it is closest to red. So obtaining this distance for all of the points from um, each centroid is the most expensive task, because at each iteration you have to do that for each of the point. Is it correct? And that is why this algorithm becomes slow. So to improve the efficiency of this algorithm, time efficiency, you can use data structures to store this data and update it each time the centroid is updated. I'm going to advance topics right now, but to make you understand why this is slow. At each point, you have to obtain the distance of a point from each of the centroid and then take the minimum. Then only you will be able to say na, this point is closest to red because it has a value of 2, from black it has a value of 5, and from blue it has a value of 3. So it is closest to red. At each point, at each time you have to obtain that. And to reduce the running time of this algorithm, you have to maintain some data structures, and there are other ways also. But yeah, to understand that, you have to understand that this is a slow algorithm. If the for bigger data sets. Is it all right? But it is a very good algorithm. Although slow, but it is a very good algorithm. Okay, so whatever I have told you is written over here. K-mean clustering, unsupervised learning algorithm, objective, key features, use cases. The steps I have written, you just go through these steps stepwise. क्लास में है अभी. Sorry. Okay, so initialize the centroid, randomly select k initial centroids from the data set. So we have talked about these steps. I'll just go through once, but I guess it is easy to understand. Assign data points to clusters, compute the distance from each point to all of the centroids, assign each data point to the closest centroid. When we have done that, then update the centroid, recalculate the centroid for each of the cluster by taking the mean of all the data points assigned to each of the cluster and repeat till convergence. Okay. What is convergence? You can specify what is convergence, that the centroid is not moving a lot, or the number of points in each of the clusters are not changing. There can be multiple ways of saying what is convergence. Centroid no longer change significantly, a maximum number of iterations is reached, and number of times, or there can be multiple ways of defining what is convergence according to you. Okay. So these are the three clusters which this data set have. I have already labeled it for you. Okay, this is cluster 1, this is cluster 2, and this is cluster 3. And you see, it didn't have any label. It labeled it itself. It is saying this is cluster 1, this is cluster 2, this is cluster 3. Now, if you think about it, now suppose there is new data, which is this or this. You can just check if this new data is closest to which centroid. Is it closest to this centroid, or closest to this centroid, or closest to this centroid? If this new data is closest to one of the centroid, you will just say that this data belongs to that cluster. Is that all right? Okay.
But Shubham,
Yes.
can there be a case that a new data is at equidistance for all the three clusters?
Yes, there can be cases. You have to decide how to break the tie.
Okay. Okay.
So we'll take a 5 minutes break and then we'll start neural networks. Okay. We will meet at 7:18. All right. So we'll talk about artificial neural network. So an artificial neural network are inspired by the structures and functioning of human brain. They consist of layers interconnected with nodes. We will see what layers and nodes are used for various tasks such as classification, regression, reinforcement learning, and so on and so forth. So whatever we have done in suppose supervised learning, you can do the same using neural network, and you can implement actually supervised learning using neural network. So if you go back and check, we used very simple, so for example linear regression, so we were using linear functions to divide our um, data into no, so for predictions, right? So for using complex data, you could think about plotting a polynomial line, so polynomial regression like squared, cube, and so on and so forth. But you have to think about that function, what function you have to use, and then you have to implement the regressions, right? So what neural networks helps us to do is it helps us obtain that function. It will not give that functional expression, but that network will represent that function. So what it will build a black box for us. You will give inputs to that black box, that network, and it will give you an output. So this is what a neural network is. It does something inside with the inputs it takes, and it will give you an output. So suppose you are doing supervised learning, you train the neural network by giving the training data. It will construct some connections between the different nodes it has. We will talk about those things, and it will make such, so it will, I'm saying make connections, but we will discuss what is making connections, and it is not technically correct, by the way. But it will do some things inside this network such that it will give you an output, and then you can check what this output is with compared to the output what you expected, right? For training testing data, you train the data, train the neural network using the training data, and then you can test it. Okay, so this is what a neural network is. It is just this network, how is this network behaving, what weights it is giving to the edges. So we'll see it. What are the characteristics? It has an input layer, hidden layer, and output layer. Okay, so forget about this. First let me draw a very simple neural network. So suppose a function is there which takes two input, x1 and x2. And this is the function g. Okay, now when we were doing perceptron model, you can remember the hypothesis was x1 comma x2. It was like this is equals to g of, I'll not write like this, it was like this actually. It was 1 and 0 if w1 w0 plus w1 x1 plus w2 x2 is greater than equals to 0, and otherwise. Remember, it was like this. It is predicting whether it is 0 or 1 when we are doing classification. Do you remember, or should I go back? Just a minute, it is here itself. Classification. So when we are doing classification, we had to say whether it is 0 or 1. So we had a hypothesis function. Where is that function? Right. So we were writing this function as w0 plus w1 x1 plus w2 x2 and w3 x3. It is greater than equals to 0, less than equals to 0. If it is greater than equals to 0, we are saying it belongs to 1 or it belongs to 0. This is what we were doing, right? The hypothesis function was this: w0 plus w1 x1 plus w2 x2. If it is greater than equals to 0, we were saying it is 1 and 0 otherwise, right? So we are just doing that. Now you see, it is taking x1 and x2 as input, and it has weights w1 and w2. We will input one more w0 to this, and this represents this hypothesis function. This hypothesis function, it takes x1 and x2 as input and gives an output which is actually w0 plus w1 x1 plus w2 x2, and this function g will just be this function. it will either give output as 0 or output as 1. If this value is more than 0, then it will give a value of 1. If this value is less than 0, then it will give a value of 1. Now this is actually a neural network right now, and we have multiple x values, right? We have multiple x1 and x2 values and labels as 0 and 1. So we have some values for this, some values for this, some values for this. What are we trying to do? We are trying to obtain the weights w1, w0 and w2. We are trying to obtain these weights. In neural networks also, they are when we are training the neural network, it means we are trying to obtain these weights w0, w1, w2. Over here also, when we are doing this classification task, our main task was to obtain the value of w0, w1 and w2, right? We were trying to obtain these values w0. So you see, we were taking input as x1 and x2, something was going on, and then we are obtaining that output. And using multiple data sets, we were trying to obtain what is the value of w0, what is the value of w1, what is the value of w2, such that if we get an x1 and x2, when we are testing, we can say that this is the label, and then we can see if it is a correct label or a bad label, right? Is it clear? Right, I hope it is clear. Okay, so you see, this is a very simple neural network with no hidden layers, right? It has an input layer and an output layer. It doesn't have any hidden layer. So this kind of functions we have already talked about when we were talking about linear functions, right? When we were talking about linear functions. But the power of neural networks, artificial neural networks, comes into play when we have hidden layers. Whenever there are hidden layers, the functions become non-linear, and then we can have complex function as well. So for example, we are talking about these kind of classifications, right? When we have red data outside and blue data inside, this kind of classification cannot be done using linear classifiers. You have to have non-linear classifiers. And when we have hidden layers in the neural network, then it is easy to see how the classification, and then it is easy to classify the data. It becomes the network becomes easy, not easy, I'll say, it becomes complex such that it can classify the data into non-linear classifications, right? So this is a neural network where we have one hidden layer, and that hidden layer has only two nodes. You see, we have edges from each of the input node to that hidden layer, from each. So from here it is going there, and from here also it is coming here. So what you can think this as a simple neural network for this one. You can think this as a simple neural network for this one, and you can think this as a simple neural network for this one. And you can obtain the weights w1, w2, w3, w4, and so on and so forth. Now, to obtain the weights, you know x1, x2, x3, and y values. You don't know the hidden values, right? You have no idea about the hidden values. You only have input values and output values. You only have input values and output values, but you have to obtain the weights of all these values. To do that, you have to do backward propagation. That algorithm is known as backpropagation. So what you do is you obtain what the loss is at this value. So you give input. So you have, suppose, n number of inputs. That column you have x1, x2, x3, and y value. You have n values over here. So you give values to this, each of the n values, and you obtain what is the difference between the value of this y and the already known y you have. You know the loss. That can be any kind of function, absolute loss function or squared mean loss error, or so on and so forth. You obtain the loss and you try to minimize that loss. When you try to minimize that loss, these weights will be obtained appropriately. So for a simple this only input layer and output layer, you can understand it very easily. You give input and you obtain what is the loss. You obtain the loss function. What you do is, when you minimize this loss, the weights of these will be obtained appropriately. Now for hidden layers, you have to obtain, so you have obtained the loss at this end. Now you have to propagate the loss over here, and then you have to propagate the loss over here. This is known as backward propagation, and we will see how it works. Before that, we'll have to understand one algorithm which is known as gradient descent. Okay, gradient descent algorithm. When we have understood gradient descent algorithm, then we'll be able to understand how we propagate the loss to the hidden layers. Okay, so first let us understand gradient descent. Okay, so we have gradient descent and then back propagation. So what is gradient descent? Have any of you heard about gradient descent earlier? Right. So it is very similar to, not very similar, the idea is very similar to local search kind of thing. Okay. So what we do is, suppose this is the loss function. So we know what the loss function is. We have a function like this, x1 comma x2, and this is actually the loss function. We plot the loss function. So this is the loss function we have. You randomly take one point and you obtain. So for this function, you can obtain the slope. The gradient for this is actually the slope, right? So you obtain the gradient. Now what you do is you move opposite direction from the gradient. So over here the slope is positive, right? This is a positive slope. So you move in the opposite direction. You move in this direction, where whatever the gradient is, you move in the opposite direction of the gradient. So you move in this direction. So you have come over here. Again you obtain the gradient and move in the opposite direction of the gradient, and so on and so forth, and you will come over here, right? So this is how gradient descent works. This is in one dimension where you have only one dimensional weight, but you can think about this as 2 dimension, 3 dimension. The one more thing to remember is the step size. So when you take the step size, suppose epsilon, and suppose you come over here again epsilon, and you come over here again epsilon, then you may have to come back. You may overshoot. You may come over here. Then decreasing step size is a good approach. So in starting, you can take a bigger step. So in the direction of the gradient, you take larger steps in the initial iterations, and as then when your number of iterations increase, you decrease your step size. Okay, so that is how you can implement a gradient descent algorithm. And why is it known as gradient? Because in this, when you have one dimensional input, it is known as slope, but when you go higher dimensions, that is known as gradient. And the gradient is the direction in which the function value increases. So over here, in the direction of the slope, the function value increases. For higher dimensions, the gradient is the direction in which the functional value increases. So you have to move in the opposite direction of the gradient. Okay. So this is what a gradient descent is. And steps is initialize the weight randomly, calculate the gradient of the loss function with respect to the weight, update the weight at the direction of negative gradient to minimize the loss. Now, can anybody tell me how are we obtaining this loss? What is this loss? What is this function f of x1 comma x2? What is this function? This is actually sum over I equals to 1 to n for each of the points. So you have x1 comma x2 points from 1, 2, 3, 4 till n points you have, and you know y. So what are we doing? We are predicting first x1 comma x2. You can just say h, not g, h minus y. So you are obtaining what is the difference for one of the values, what is the loss in one of the values, and you are summing it up for all the n values, right? So this is what loss is. You say what did I predict? I predicted h x1 comma x2, but originally it is y. So this is the difference it has, and we sum it over all n, and then this becomes the loss function. All right. I'm just saying x1 comma x2, it can be x1, x2, x3, x3, 4, xn till it can go to n dimensions as well. And you can take this as m number of values and n dimensions. Okay. So when we take the gradient of this whole function where we are, yes.
Summation over I. The I is not in the equation. Can you please mention I in the equation so that
I,
the
huh,
equation can better be understood?
yes, yes.
H of I x1
It will not. Yes, I'll write it properly. It is not h of I. I'll write it properly. See, it is like this. Summation. Write it properly. I am writing capital X for the vector X. Sum over I is equals to 1 to n, 1 to m, where m is the number of values you have for training, h of x I minus y. So this is the function you have, right? X is a vector. X is a vector. Is it all right? Okay. And this I represents the row you are at. I represents the row. Now, you see, when you are taking gradient, you are taking at each of this value and then summing it up. For loss also you have to take it for each of the values and sum up. For gradient also you have to take for each of the values and then sum up. So you have first element plus second element plus third element, and we are taking the gradient, you have to take it for all, right, for each. So this becomes expensive if this m is very large. If this m is very large, taking gradient for each of the training points becomes expensive. To decrease this, there are different variants. First is the batch gradient descent, where you take sum of the entire data set. Stochastic gradient descent is update the weight for each point. So what you do is take gradient of only one point. Don't sum it up. You obtain the gradient and then move to that gradient opposite direction of the gradient. Then again take another point and move to the obtain that gradient and move in the opposite direction of that gradient. In originally what we are doing is we are taking the gradient of each of the point, summing the gradient up and then moving in the direction opposite to the summed up gradient. But in stochastic gradient descent, we are not taking the gradient of all the points. We are taking the gradient of only one point and we are moving in the opposite direction. It may not be correct, but it is faster, right? Mini batch gradient descent. Mini batch gradient descent, it don't take gradient of all m's. You take gradient of a small batch. Take suppose four numbers, four inputs, and take the gradient of only four. So this is also faster than the batch gradient descent, where you are taking the gradient of all of the points, right? So these are the variants of gradient descent. It is just improving the running time of the gradient descent algorithm. Is that all right? Saurav, Sikhar? If it is difficult to understand, I'll re-repeat because I think I'm going fast maybe. Saurav? Okay, so I assume it is all right. Okay, so I'll just reiterate over here. So suppose this is not a one-dimensional problem, suppose it is an n-dimensional problem. So for this point, this is a compound function, right? It is a function summing up for all of the losses, for loss of first row plus loss of second row plus loss of third row and so on and so forth. And when you want to take the gradient at this point, you have to take the gradient for this row, then for this row, for this row. When you have obtained the gradient for all and obtain the sum of the gradient, then only you can move from this point to the next point. Otherwise you will not be able to move. Again, when you have moved over here, for again for the gradient, you have to obtain the gradient for each of the rows, sum it up and then move in the new direction, right? What stochastic gradient descent is doing is it is saying you don't need to obtain the gradient of all because you have so many data and you can do many number of iterations. What you do is you take only one point, take the gradient and move. Don't take the gradient of all the points, sum and so on and so forth. It is quite fast and it does well. It performs well by the way, stochastic gradient descent. And mini batch gradient descent is an improvement over stochastic gradient descent where you're not doing just only one point, you are doing it for some number of points. Okay, so this is how gradient descent is. We have, yes.
Shubham, can there be a situation where plus epsilon plus epsilon and minus epsilon have same slope value?
Same slope.
Slope value.
So there is a plateau over here. Like,
Except that means
yes,
uh,
yes, you can have a function like this.
yeah,
Yeah,
exactly.
you can have a function like this.
So in which direction am I supposed to move to find out what can
What
we
will
say?
happen over here is the gradient descent will fail if the step
Ah,
size is not
ah,
large
okay,
enough.
okay, okay,
You
okay,
will not
okay.
be able to obtain the gradient at this point.
Means for a gradient descent to apply, the function shall be in non-step function.
So when we know this function, right, we are defining
No,
this
no,
function.
because it is known. But many times when the data is in this form, then we cannot apply gradient descent rule.
Just a minute. We are actually defining the loss function. We are saying we will obtain mean squared error. So I am writing this. This is what? Okay, this is mean squared error. I have written it. Well, this is what the loss is. Mean squared error. Right, so a square would be there. Sorry for that error. Square. So this function I am defining, and I know it doesn't have that form, this step form. It doesn't have that form. I know this function is a curve. I am obtaining the gradient of this function, right? I know the structure of the function. It is up to me how to define the loss.
Okay, okay, ठीक है. Okay.
अच्छा, by the way, यहाँ
Means
square
for,
है.
for known functions, only gradient descent can be applied. Is it like that?
That is not true. Gradient descent can only be applied to a function which has a which is differentiable. If that function is not differentiable, you cannot obtain the gradient of that function. For example, when we apply this local search to some meta heuristics, we don't know what the function is, objective function is. In optimization also we have an objective function, right? And we have some constraints, right? And this objective function may not be differentiable.
I couldn't get you. Please repeat it once again.
So when we perform optimization, we have an objective function and we have constraints, right?
Yes, yes,
For
yes.
example, for example, integer programming problems. When we have integer programming problems, for example, traveling salesman problem or many problems we have talked about, knapsack problem, those objective functions which we have are actually not differentiable because it is a integer programming problem. It is not differentiable function. The objective function is not differentiable because
No,
it is
not.
in.
How could means how in the instant case are you defining differentiable function and non-differentiable function?
So you have to go and see the properties of when a function is differentiable or not.
No,
Over
how
huh,
generally we define differentiability if
so
x means f of x is differential if f of x minus f of x plus h upon h limit h tends to 0,
I will tell
it's
you.
0.
Just a minute, I'll tell you. So you see, when we talk about knapsack problem, right? So when we are talking about a knapsack problem, so it has a structure of reward times whether you are selecting that object or not. Ri times w. If you know, don't remember, I'll just write the reward knapsack problem. So what is the objective of that knapsack problem? It is r1 times x1 plus r2 times, it is r2 times x2 plus dot 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 rn times xn, where xi represents whether object I has been picked or not, right? And you see these value 0, it can either be, so xi can either be 0 or 1, right? So this function can take discrete values, either it will be 0 or it will be 1, it will be 7, it will be 8, it will be 30, and so on and so forth. It is not a continuous function.
Okay.
So when it is not a continuous
discrete.
function, it is not a differentiable
So,
function.
so a problem whose output is discrete cannot be differentiable. Is it like
Right.
that?
Yes, because you know it is a discrete function. There is no continuous curve. Continuity is necessary for differentiability.
Okay.
Therefore, we will not be able to use gradient descent to minimize this function. And hence we go for local search.
Okay. 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 ठीक है. Hmm.
Okay. So we have talked about activation function. Yes.
Can we conclude that for the functions which are discrete and for the function similar to step functions, the gradient descent function, rather for the functions which has zero slope, we cannot apply gradient descent through gradient descent function.
For step function also you'll not be able to apply gradient descent
Yeah.
because it has corners, right? It is not differentiable at that point.
Okay. Yes. Correct. So that's what I am concluding for discrete functions and for the functions which are similar in step function nature, gradient descent cannot be applied.
Simply put, if a function is not differentiable, you'll not be able to use gradient descent.
Okay. 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 For a
Not
for continuity is necessary for gradient descent functions.
nahi, differentiability is more important. Differentiability
Sorry. Differentiability is
necessary.
necessary for gradient descent.
Uh,
Okay. 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 Yeah.
okay, so we were talking about activation and backpropagation. Okay, so backpropagation, first activation is what, and we will talk about the first backpropagation. So you see, when we are obtaining this loss, we were only able to obtain the loss at this point, right? Because we know y values, we know the y values, and then we can obtain the loss. At this stage, you will not be able to obtain the loss because you don't know what is the h1 value. These are just we have put these nodes there. You can have 2 nodes, you can have 4 nodes, you can have 10 nodes. It's up to you how you're designing the network. So the gradient, the loss can only be obtained at this node because this output is known. We don't know the output over here. Then how will we use gradient descent? Because if we don't know the loss function, we will not be able to obtain the gradient. So backpropagation is a way to obtain gradient at each of the layers, at each of the layers, right? So what will we do is, the idea is very simple. You see, we have, so what are we doing? We are saying this is W1 and this is W2. And suppose, so what are these? These are actually obtaining some, these are actually some values. This is X1 is some value in R, right? It is some value in R. This is some value in R. This is some value in R, right? These are some values. So over here, these will also have some values. Actually, it is a function. This is H1 is also a function which has a which gives a value, real value, right? So what we are doing is we are saying this h1 times w1, w1 times h1 plus w2 times h2 is actually y. Some function of this is actually y, right? So we have obtained the loss over here using this w1 and w, sorry, h1 and h2 and w1 and w2. You can obtain the loss as at g. So we are propagating the loss from this end to this end. Again, if there are some more layers over here, when you have obtained the loss from here to here, you can use this loss to obtain the loss from here to here. We are just back propagating the loss using the functional value we have. So that is the idea. A lot of mathematics is involved. I'm not going into the mathematics. The idea is to propagate the loss from the output node to the inner layers. That is the idea of backpropagation. And at each of the node, we are using some activation function. So we have talked about this. So whenever there are some inputs and that input go to one of the node, at that node we use an activation function. It takes the value, any input to 0 to 1. And that value will be defined by this function. And this h when we are writing h1, this is some activation function, either sigmoid function or uh, ये ReLU, ReLU, ReLU function or tanh function, some function which converts the input, whatever the input is, to 0, 1. And h1 is one function, h2 is one function, and so on and so forth. So what is y? Y is w1 times h1 function plus w2 times h2 function plus and w naught. That is known as a bias, plus w naught. So this is the idea of back propagation. Now what I'm trying to do is, I have completed whatever I have over here. I'll show you TensorFlow from Google. It will give you an idea of how this works, and you can play around with that also. So what is the last slide I have? It is application image. We will see one application in the next class, natural language processing and so on and so forth. This is all right. What I will do is, I'll just start screen sharing over here. Is my screen visible?
No, your screen is not visible.
I guess
No,
right.
visible.
Okay, so this is one platform made by Google. Just a minute. Huh. Right. So it is known as Playground. Playground.tensorflow.org. If you come over here, what you can see is you have some data. These are some of the data it has. So you can see the visualization over here. So this is two categories. This is, again, only two categories are there, but these are some of the data it has. So we can take any, suppose we are going for this data, and this is a network I have. So suppose I'm just deleting all the networks I have. So just make it no hidden layers. Okay, so this is the input and this is the output. So this is just a linear classification. I'm trying to classify using linear function. What is this function? This is this line, and this function is this line. Okay, these are just linear functions, and we'll see if it is able to classify this data using just linear functions. It has two linear functions, this linear function and this linear function. So when I play, you see what it is doing. It is trying to minimize this loss. So the test loss was this, the training loss is this. It is not able to decrease the loss from 0.5. You see this, what is this epoch? It is number of iterations it is doing for the total um, data set. So we are able to see that linear functions are not performing good. The loss is stable and it is not decreasing. So what we'll do is we'll add one layer, and we have only um, two nodes at this layer, and we'll just run it. So you see it is trying to, so what is this doing? This is this kind of function, this is this kind of function, this is this kind of function, and this is this kind of function. Okay, so it has done somewhat. What we'll do is we'll try to add more layers. Suppose we have added one more layer, and now we'll see what is happening. So you see it has classified it very nicely. If you add more neurons over here, you see it is becoming more smooth. You can add more layers, add more complexity to this, and you can see what it is doing. So this is how these hidden layers are making the classification non-linear. Earlier it was linear classification, but now it is becoming non-linear classification. You see, this was linear, this was some was linear, but this is not linear. You see, this is non-linear. Over here, this function, whatever this function is at this node, it is non-linear. This is non-linear, and ultimately this is the output, which is like this. And you see the test loss is very close to 0.003. We can just stop this. You can use another data set, and let us use the same network. What it is doing is it is classifying very nicely. You see, again you can go for another data set like this, and you can just see it is classifying very nicely. Maybe a lot of nodes we have used, we can decrease some of the nodes. Maybe not two hidden layers is required, only this will, yeah, this is able to classify it. So unnecessarily making your network complex is also not desired. That is also one design aspect. You have this also. So let us see if this is able to do it or not. So you see this is not able to decrease the loss a lot. So let us add some more layers over here and let us see if it is able to do it or not. So you see what we are seeing is that linear functions are not able to classify this properly. We can add non-linear functions also. So let us add, this is a non-linear function. Let us add some more non-linear function just for, we are just playing over here, and let us see what it is doing. You see it is classifying very nicely, the classification, but the loss is fluctuating. So maybe we can decrease some of the nodes and we can just plug and play. It's just plug and play. You'll be able to visualize what is happening. Okay, so this is the last thing I wanted to show you. Any questions?
No.
All right. So this was planned for today. The next class will be on next Sunday, and I guess I will wrap up on that class. Okay, we will complete neural networks, and I'll start with um, natural language processing, and I'll wrap the course in the next class. Okay, thank you. I'll end the meeting now.